Welcome to Agentic AI World, your daily interview prep for senior AI engineering roles. I'm your host, and today is episode 71. Today's topic, AI gradient descent and optimization, how senior engineers master the math of model training. Let's get into it. Section 1, why optimization is the core skill. Here's a question you will almost certainly get in a senior AI interview. Walk me through how a model actually learns. The shallow answer is gradient descent. You update weights to minimize loss. But the deep answer is what separates a senior engineer from a junior one. It's understanding why vanilla gradient descent fails at scale, what optimizers actually do, and how to choose, tune, and debug them in production. Let's build that deep answer right now. Section 2, gradient descent, the foundation. Gradient descent is simple in theory. You have a loss function, a number that measures how wrong your model is. You compute the gradient of that loss with respect to every parameter in your model. That gradient tells you which direction increases the loss. So you step in the opposite direction. The update rule is theta equals theta minus learning rate times gradient. You repeat this until the loss stops improving. 3 variants exist based on how much data you use per step. Batch gradient descent uses the entire dataset per update. Accurate, but slow and memory-hungry. Practically useless for deep learning. Stochastic gradient descent, SGD, uses a single example per update. Fast but noisy. The updates are so erratic that convergence is unstable. Mini-batch gradient descent is the standard. You use a batch, typically 32 to 512 examples, per update. You get a reasonable gradient estimate without blowing memory. In practice, when someone says SGD, in a deep learning context, they almost always mean mini-batch SGD. Section 3, the problem with vanilla SGD. Vanilla SGD has 4 major failure modes you need to know cold. First, the learning rate dilemma. Too high and you overshoot. The loss oscillates or explodes. Too low and you barely move. Training takes forever. There's no single learning rate that works everywhere. Different parameters need different step sizes. A parameter that rarely gets updated needs bigger steps. A parameter updated every batch needs smaller ones. Second, saddle points. In high-dimensional spaces, saddle points are far more common than local minima. A saddle point has 0 gradient, but isn't a minimum. It's a minimum in some directions and a maximum in others. Vanilla SGD gets stuck because there's no gradient to follow. Third, ravines. Imagine a lost landscape that's like a long, narrow valley. SGD oscillates side to side across the ravine instead of moving efficiently toward the minimum at the bottom. Fourth, slow convergence. Because all parameters share a single global learning rate, you can't adapt to the geometry of the lost landscape. These aren't academic problems. They're why model training stalls, diverges, or takes weeks instead of hours. Section 4, momentum, solving oscillation. The first fix is momentum. Instead of updating with just the current gradient, you keep a running average of past gradients, called velocity, and add it to the current update. Velocity equals beta times velocity minus learning rate times gradient. Theta equals theta plus velocity. The beta term, typically 0.9, means you remember 90% of your previous direction. This smooths out the oscillations in ravines and gives you a speed boost in consistent directions. Think of it like a ball rolling downhill. It doesn't stop and change direction every step. It accumulates speed in the direction of persistent gradient. Nesterov accelerated gradient, NAG, improves on this by computing the gradient at the look-ahead position, not the current one. It's a subtle but meaningful improvement. You evaluate where you're going to be before deciding how to step. NAG converges faster than standard momentum in many settings. Section 5, adaptive learning rates, RMSProp, Adam. The real breakthrough came with adaptive optimizers. These automatically adjust the learning rate per parameter based on gradient history. AdamW was first. It accumulates the sum of squared gradients for each parameter. Parameters with large accumulated gradients get smaller steps. Parameters with small accumulated gradients get larger steps. This was great for sparse features, like in NLP, where certain words appear rarely. Their gradients are small and infrequent, so AdamW gives them bigger updates. The problem, the accumulator only grows. Eventually, every learning rate shrinks to near 0, and training stops. Grad dies in long training runs. RMSProp fixed this with an exponentially decaying average of squared gradients, like momentum, but for the gradient squared. The accumulator doesn't grow forever. Training stays alive. Then came ADAM, adaptive moment estimation. ADAM combines momentum and RMSProp. It keeps two moving averages. M, the first moment, is the exponentially decaying average of gradients. This is your momentum term. V, the second moment, is the exponentially decaying average of squared gradients. This is your RMSProp term. The update rule divides the momentum-adjusted gradient by the square root of the second moment, plus a small epsilon for numerical stability. The critical detail, bias correction. Early in training, M and V are initialized to 0. They're biased toward 0 for the first few steps. ADAM corrects this by dividing by 1 minus beta to the power of the current step. ADAM with default hyperparameters, beta 1 0.9, beta 2 0.999, epsilon 1 times 10 to the power of -8, works remarkably well out of the box. It's the default choice for most deep learning. But ADAM has a flaw. It can converge to sharp minima that generalize poorly. SGD with momentum often finds flatter minima that generalize better, which is why many production models finish with a phase of SGD after ADAM pre-training. AdamW fixes ADAM's weight decay bug. Vanilla ADAM folds weight decay into the gradient, which interacts incorrectly with the adaptive learning rate. AdamW decouples weight decay from the gradient update and applies it directly to the parameters. This is now the standard for large language model training. Section 6. Learning rate schedules. Even with ADAM, the learning rate schedule matters enormously. Cosine annealing starts high and decays following a cosine curve to near 0. Clean, effective, widely used. Warmup plus cosine is the standard for transformer training. You start with a tiny learning rate, sometimes 0, and ramp up linearly for the first few thousand steps. This prevents early instability when gradients are noisy and the model is far from a good region. After warmup, you decay with cosine. One cycle policy, popularized by fast.ai, ramps up to a maximum, then decays. Trains faster because the high learning rate phase explores the lost landscape aggressively. Then the low phase converges cleanly. Linear decay and step decay are simpler schedules that cut the learning rate by a fixed factor at fixed intervals. Less principled, but still effective in practice. The key insight: the learning rate is the most impactful hyperparameter you control. A model trained with the right schedule will outperform the same model trained with a flat learning rate almost every time. Section 7. Gradient pathologies and how to fix them. 3 gradient problems come up in every deep learning interview. Vanishing gradients. In deep networks, gradients are multiplied through every layer via backpropagation. If those multiplications shrink the gradient, as they do with sigmoid and tan activations, by the time the gradient reaches the early layers, it's nearly 0. Those layers don't learn. Fixes: use ReLU or its variants. They don't saturate for positive inputs. Use residual connections. The skip connections in ResNets let gradients flow through the network without passing through every activation. Use batch normalization to keep activations in a healthy range. Exploding gradients. The opposite problem. Gradients grow exponentially through deep layers or through time in recurrent networks. Training diverges. The standard fix: gradient clipping. You compute the gradient norm, and if it exceeds a threshold, you scale the gradient down so its norm equals the threshold. This is applied universally in LLM training with a typical clip value around 1.0. Dead neurons. ReLU outputs 0 for negative inputs. If a neuron's weights drift such that it always receives negative input, its gradient is always 0. It stops learning entirely. It's dead. Fixes: leaky ReLU lets a small gradient through for negative inputs. YeLU and Jello have smooth behavior near 0 and rarely die. Careful initialization and small learning rates also prevent neurons from dying in the first place. Section 8. Second-order optimizers and their trade-offs. First-order optimizers use only gradient information, the first derivative. Second-order methods use the Hessian, the matrix of second derivatives, which tells you about the curvature of the lost landscape. The most famous second-order method is Newton's method. It uses the inverse Hessian to scale steps precisely to the local curvature. It converges much faster than gradient descent in theory. The problem: the Hessian has as many entries as parameters squared. For a model with 100 million parameters, the Hessian has 10 to the 16 entries. Computing and inverting it is physically impossible. Quasi-Newton methods like LBFGS approximate the Hessian using gradient history without actually computing it. They work well for small to medium models, but still don't scale to the billions of parameters in modern LLMs. Natural gradient methods use the Fisher information matrix instead of the Hessian. It captures the geometry of the probability distribution rather than just the loss surface. KFAC is the practical approximation, used in some research settings, but not mainstream production. For production AI today, stick with AdamW with warmup and cosine decay. Second-order methods are fascinating but impractical at scale. Section 9. Production debugging. How to diagnose optimization failures. This is what actually matters in a senior interview. Not just knowing the algorithms, but knowing how to debug them. Loss explodes early, learning rate too high, gradient clipping too loose, or bad initialization. Drop the learning rate by 10x. Add clipping at 1.0. Check your weight initialization scheme. Loss plateaus and won't move. Learning rate too low, optimizer momentum too high, or you're stuck at a saddle point. Try increasing the learning rate. Add noise via higher batch size variance. Loss oscillates without converging, typical ravine problem. Increase momentum. Switch from SGD to Adam. Add gradient clipping. Loss decreases in training, but validation loss diverges. You're overfitting. This isn't an optimizer problem, it's a regularization problem. But optimizer choice matters. SGD often generalizes better than Adam because it finds flatter minima. Training is slow, batch size too small, learning rate too conservative, or you're using a suboptimal optimizer for your architecture. Profile your gradient norms per layer. If early layers have near zero gradients, you have a vanishing gradient problem, not a slow optimizer. The gradient norm is your vital sign. Log it every step. A healthy training run has gradient norms in a consistent range, not exploding, not vanishing, not dropping to zero. Section 10. Interview master points. Let me give you 5 things that will impress any interviewer. 1. Know the Adam bias correction formula and why it exists. Most candidates just say Adam uses moving averages. The bias correction detail signals deep understanding. 2. Explain why AdamW exists. The distinction between L2 regularization and weight decay is subtle. Knowing that vanilla Adam applies them wrong and AdamW fixes it marks you as someone who reads papers, not just tutorials. 3. Know when not to use Adam. If generalization matters more than convergence speed, which it does in most production settings, finishing with SGD or using AdamW with strong weight decay is often better. 4. Gradient clipping is not optional for large models. State this confidently. Every serious LLM training run uses gradient clipping at the global norm. 5. Learning rate warmup is load-bearing infrastructure for transformers. Without it, the first few gradient steps can be so noisy that they permanently damage the model's ability to learn. This is why every transformer paper mentions warm-up steps. Conclusion. Let's wrap up. Optimization is not just gradient descent with a tunable learning rate. It's a system, gradients, momentum, adaptive scaling, schedules, clipping, and initialization that has to be engineered deliberately. Senior engineers don't just run Adam and hope. They monitor gradient norms, tune warm-up, use weight decay correctly, and know when to switch optimizers to improve generalization. That's the mental model you take into your next interview. This has been episode 71 of Agentic AI World. If this helped you think more clearly about how models actually learn, subscribe. We drop a new episode every single day. I'll see you tomorrow.